Welcome to section 9.3. 9.3 are on what are called relative rates of growth. And the basic idea of this is really strongly related to our end behavior models. Um, because when we decided on end behavior models, we always had to pick what part of a function is growing fastest, because that takes over as x is going off to infinity or negative infinity. Uh, well, we can do this with entire functions as well. And the idea of this is I want to do a comparison, in other words, a ratio, and then take the limit of that ratio as x goes to infinity. So if I want to compare functions f and g, it doesn't matter which one goes on top, but if when I do the limit as x goes to infinity of f over g, and that's infinity, that means f is growing faster. Uh, Here, because I'm saying that g is growing slower, if when I do the comparison as x goes to infinity, I get 0, that means the top is growing slower. So if in the comparison, the limit of the ratio as x goes to infinity is equal to infinity, top is growing faster. If that limit is going to equal 0, then the top is growing slower, or the bottom is growing faster. The way I know that they grow at the same rate would be if I then get the limit exists and is some number that's not 0. So some examples of this. Uh, and most of these are ones that we can pretty easily tell which one's bigger or not. This is just to give you an idea of how this works. So if I'm looking at e to the x and x squared and I wanted to compare these, well, I can do the limit as x goes to infinity. And it doesn't really matter which one goes on top. Usually the one I think is growing faster, I stick on the bottom because I like it when my limit is equal to 0 or something finite. I don't like dealing with it going off to infinity, but it doesn't matter. Uh, so I'm going to say x squared over e to the x. And these both go to infinity. My limits as x goes to infinity, so I could use L'Hopital's rule. So there's the limit as x goes to infinity of 2x over e to the x. Still going to infinity over infinity, so I can do L'Hopital's rule again. Limit as x goes to infinity of 2 over e to the x. And then as x goes to infinity, this is 0. So e to the x is faster. If I wanted to compare the natural log of x and x squared, well, I can do my limit as x goes to infinity of natural log of x over x squared. Now, these are both going, I have infinity over infinity, so I can do L'Hopital's rule, which is an awesome thing to have here. Simplifying this compound fraction, that's the limit as x goes to infinity of 1 over 2x squared, and that's 0, so my natural log of x is, oops, sorry, not natural log of x. Uh, my x squared is faster. Since my limit was 0, the bottom one is faster. And then finally, if I wanted to compare x and x plus sine of x, so as this is going off to infinity, uh, this is a little bit tougher here. Uh, so I'm going to split this into two fractions. And so this would be my limit as x goes to infinity of x over x, which is 1, plus the sine of x over x. Well, the limit of 1, no matter what x is going to, is 1. And we did sine of x over x as x goes to infinity back in chapter 2. That's 0. And so this equals 1. And so these are growing at the same rate because that limit isn't 0, it's not infinity, and it does exist.